Hey, it's Wakefield coming at you from day 8, I think, of the End Times quarantine. Kind of feels like day 800. I don't know, man. So, I realized I got to get 10 more lectures out of these last, set and a half of slides. So, woo for that. But today we're going to start talking about carboxylic acid. This is going to eat up a large part of what's remaining and is going to just generally be super dense in terms of mechanisms and whatnot. So, right. Now, you know what a carboxylic acid is because, you've been paying attention. Right, that's going to be a carbonyl carbon double bonded to an oxygen. And then you're going to have an OH and a carbon attached to that carbonyl carbon, right? OH on this side, carbon on this side. Carboxylic acids exist in two resonance forms, right? We can take the lone pair on our oxygen and it can push down, push electrons up, and that's going to give us this structure here with an O minus and an O plus, right? As the name implies, carboxylic acid, right? Carboxylic acids are able to relatively easily lose their proton and make O minus plus H plus, right? This negative ion they form is called a carbox. I'll try that again. It's called a carboxylate ion. And so carboxylic acids are significantly more acidic than alcohols, right? Because if we compare the two, right? Say we have an alcohol and it loses a proton, O minus plus H plus. Now we have a carboxylic acid and we do the same thing. You're going to get O minus and H plus, but the carboxylate is stabilized via resonance. I'm able to move that negative charge to the other oxygen, making O minus like this. So this negative charge is spread out across two oxygens instead of being stuck on just one oxygen. So that's why carboxylic acids are more acidic, is because the anion that you generate is more stable than, let's say, the anion you get from generating an alkoxide from an alcohol. So these guys here are stable. We're going to have to hang a drawing, writing with this thing. Stable via resonance, right? Those two charges move back and forth. Structure can impact acidity. So anything that we do is going to make that carboxylate more stable, that's going to make that O minus more likely to occur, is going to make our acid more acidic. So the thing that we see most doing this is alpha electron withdrawing groups. So you have your carboxylic acid and you have some electron withdrawing group. And this is more acidic than just the plain carboxylic acid. Why is this? When you have your electron withdrawing group, it's going to pull electrons towards itself, typically inductively, right? Just through the carbon electron withdrawing group bond. We're going to pull electrons towards itself, which in turn is going to make this carbon here a little positive, which in turn is going to lead that carbon to pull electrons towards itself, right? Pulling electrons away from the carbonyl carbon. Carbon gets a little bit more positive, which in turn is going to pull electrons away from our oxygen, right? So since everything's a little positive and pulling electrons away from that oxygen ever so slightly, that's going to lead that oxygen to be able to more readily form a negative charge. So, right, you've got all these things pulling electrons away. You get this electron withdrawing group pulling electrons towards itself, which in turn has the carbon it takes electrons from, pulling electrons towards it, right? That this is easier to form. Let's try to put that someplace where I can actually write the whole sentence I wanted to write. This is easier to form with an electron withdrawing group. So if you have an electron withdrawing group on your molecule, the carboxylate is just easier to form, right? So the more electron withdrawing groups you have, the more acidic your carboxylic acid is going to be. So we can do this, right? So we can look at this by saying, hey, if I have a fluoride and then I have 3 fluorides, right? This is going to be more acidic because it has more electron withdrawing groups, right? It has more things pulling electrons toward themselves than just this one group here, right? You can also look at this kind of based on how good of an electron withdrawing group you have. Halogens, I think, are just the easiest, right? So we have Cl, we have chloroacetic acid, and bromoacetic acid, right? This is more acidic because Cl is more electronegative than Br. Right, so the chlorine is a better electron withdrawing group and pulls electrons away from the carbonyl carbon and thus the OH oxygen better than bromine does. To kind of illustrate this, now I'm never going to make you memorize these numbers, but it's just a way to illustrate the impact that electron withdrawing groups can have on acidity. Right, we can look at acetic acid, which has a pKa of 4.74. And then you can look at trifluoroacetic acid, which is the same thing, but the hydrogens on the alpha carbon have been replaced with fluorines. This has a pKa of 0.23. Now, this is just vinegar. I don't know. Vinegar, I don't know. Now we get to me not being able to spell, just like I'm there. This is vinegar. This is not vinegar. So acetic acid, tasty on French fries. Pretty good as a potato chip seasoning. Salt and vinegar, A+, good times. Trifluoroacetic acid, definitely not. So the difference between 4.74 and 0.23 is roughly about 10 to the 4th times as acidic. So remember, pKa is a logarithmic scale, so every number is a factor of 10. So trifluoroacetic acid is about 10,000 times more acidic than acetic acid. Now, Do I have a story for this? Of course I do. And why should you be denied the story while you are also denied human contact? So here we go. When I was in graduate school, we had a summer research student, an REU student, come from Stony Brook to the University of Pittsburgh. And when she got there, I noticed that she had a scar that ran from her elbow down to her wrist. And I was like, yo, what happened? It wasn't quite like that. It wasn't quite that like insensitive, but you know. And she was like, oh, so when I was in my peptide synthesis class, we were using trifluoroacetic acid. And my professor was like, hey, this stuff's really dangerous. Let me use it so we don't have to worry about you guys messing anything up. Well, he sucked it up into a glass pipette, and trifluoroacetic acid has a low vapor pressure, kind of like dichloromethane. You know, when you suck dichloromethane up into a pipette, it wants to like shoot itself back out. That's because the dichloromethane is evaporating and building up pressure in the pipette bulb, which causes it to shoot out. Trifluoroacetic acid does the same thing. So he sucked up the trifluoroacetic acid, and it shot out of the pipette and hit her on the arm and burnt her all the way down her arm. Now, I'm not there, but I know that probably half of you went, damn, I would have got my school paid for. Which is the normal response that everyone has is, I gonna get paid. I don't know if she got paid or not. I didn't ask the follow-up of like, why are you still working? You should be set now. But, so, acetic acid, good on French fries. Trifluoroacetic acid melts the French fries. So just those three fluorines really change how the molecule behaves. All right, so now we're going to talk about what happens when you treat acids with bases and what we end up with there. All right, so when you have a carboxylic acid and you treat it with a base that has a metal, say random metal hydroxide, right? You're going to get O metal, and you're going to make water. Right, from Gen Chem, right, it's always you make, when an acid and a base react, you always make a salt and water. Lo and behold, you make a salt, and you make yourself some water. I'm not going to insult your intelligence by labeling H2O as water. All right? So these are called metal carboxylates. So the name changes based on what the metal is, but if it's just a generic metal, we'll just call it a metal carboxylate. Right. We can also do this with amine bases. We're going to use ammonia as our base because it makes the naming easier for you. This is called an ammonium. Let me make that look better here. There you go. This is an ammonium. Carboxylates. I'm going to get used to writing with this stylist. I promise. No. Okay. Right. So NH4, that is an ammonium. Right. So the naming convention is you put the positive ion first, and then you put the carboxylate. So that is our naming convention. We'll go over actual naming here in a second. So let's talk about these as hydrogen bond donors. Ooh, that could have been bad. Donors and acceptors. All right. So we look at a carboxylic acid. You have an oxygen, has a lone pair. This is an H bond acceptor. And then you've got an OH, which is an H bond donor. So you have both hydrogen bond donors and hydrogen bond acceptors in the same molecule. So under certain conditions, you can actually have your carboxylic acids a hydrogen bond together. Right, and they'll form a dimer where they are stuck together. The fact that we have two parts of our molecule that can hydrogen bond, right? Oops. This leads the hydrogen bonding leads to high boiling points, right? Because you have a lot of interactions holding your molecules together, right? Holding the liquid together. So now we're going to talk a little bit about naming. Right, so the naming for these is pretty easy. You're going to remove the E from the hydrocarbon name and add oic acid. Right, I guess I should have given you the slide there, but I have faith in you. Right, so this has 4 carbons. It's going to be butanoic acid. Your acid is always number 1. It always is going to be the first carbon in your chain. So we've got 1, 2, 3, 4, 5, 6. This is going to be hexane oic acid, and then 1, 2, 3, 4. 4-methyl hexanoic acid. All right, so now let's have you play along. All right, so what would our longest chain here be? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then this one is also 1, 2, 3, 4, 5, 6, no matter which way we go. So we're going to go with the orange dots, right? Because this is the longest chain that also contains our functional group. So this is going to be hexaneoic acid. And then we're going to have 4 ethyl. Oh, forgot my dash. 4 ethyl 2 methyl hexanoic acid. So naming carboxylic acid in a straight chain is pretty easy. The big thing, remember, is that you're going to have your acid be number 1. That slide I promised you that I should have showed you before. So now we're going to talk about when you have a ring that contains a carboxylic acid. We're going to name this just like we did kind of aldehydes, because you can't have a carboxylic acid in a ring. You can have it on a ring. So we can have something like this, where your acid is hanging off of your ring, right? So here we're going to name the ring. So this will be cyclohexane. And then the acid part, we're going to do the same thing we did with the aldehydes, and it's going to be carboxylic acid. So this part of it here is encompassing that carboxylic acid is hanging off of the ring. So just like with aldehydes, the carbon that has the acid is carbon number 1. Right? So this is going to be your number 1 carbon. So we're going to name our ring, ignoring the carboxylic acid for now. This is going to be 4 ethyl 2 dimethyl. Oh man, this is not going to work. We'll come down here. Cyclobutane carboxylic acid. Like, you guys have known that, whiteboard management has not been, my best skill. And now I've got to learn how to manage a whiteboard. Oh, that's my iPad? Like, come on now. This is not cool. So this is carbon number 1, right? 2 and 4, 2, 3, 4. Right, this one gets to be 2 because it's 2, 2, 2, 4 versus 2, 4, 4. Right, so you always want to make sure that that second number you're going to have as the lowest possible number as possible, because both of your first and last numbers are going to be 4. Right, and then we have dicarboxylic acids. Right, so something like this. Right, it's just what you would expect. It's going to be dioic acid. So 1, 2, 3, 4, 5, 6. I swear I can draw stuff that it's not just 6. So hexane dioic acid, because we have 2 carboxylic acids. You don't need to number the acids because we know they're at the end. But if you had, let's say, this is definitely longer than 6. Make it easy. Right, if we had this, right, our longest chain is 1, 2, 3, 4, 5, 6, 7, 8, 9. So going to be nonane dioic acid. Oh man, so close. But now I've got a choice. Do I number it the green direction or do I number it the orange direction? You number it the orange direction to give your methyl group here the lowest possible number. So this is going to be 2-methyl nonane dioic acid. Hey, not 9 again. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. This is going to be octane dioic acid. And am I going green or am I going orange? Orange gives us 1, 2, 3, 4. Green gives us 1, 2, 3, 4, 5. So we're going to go orange. So this is going to be 1, 2, 3, 4. 3-propyl octane dioic acid. So not too bad. So next up, we're going to talk about how you name carboxylate salts. So the big change here is twofold. One is what we said before is your positive ion comes first in the name. And instead of having oic acid at the end, it's going to be something, make it the scientific blah, O8. So we're going to change the oic acid ending on our acid name to become an O8 to denote, this denotes negative charge, right? The 8. Great, so let's start at something simple here. So I have a metal carboxylate here. We've got lithium as our positive ion. That comes first. So it's lithium, and then we have 1, 2, 3, 4. It's going to be butan. And now if the lithium was a hydrogen, it'd be butanoic acid. But because the lithium and not a hydrogen, and this whole piece here, this whole piece is negative, it's going to be butan-O8. I leave these relatively simple for you. So this is 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6. So this part here, like we discussed before, that is an ammonium. So this is going to be ammonium. And then 1, 2, 3, 4, 5, 6. Still 6. Hexan O8. Right, so we're going to have ammonium hexanoate. So yeah, I want to point out, I didn't point this out before. These two things are not bonded, right? The nitrogen is positive because it's making too many bonds. So it doesn't have an orbital available to make a bond to the oxygen. So what's happening is the ammonium is just hanging out by the negatively charged oxygen as opposed to trying to make a bond to it. So it's a little bit different than what you kind of see with the metals. All right, so these have been some pretty straightforward examples. I'm not going to dress it up too much because, whatever. But what if we have a substituent on our group here? So, let's not make it an acid. Let's make it carboxylate. So still the metal goes first. And then you name the whole rest of it. basically as if it were an acid. So you have 1, 2, 3, 4, 5. So this will be 5 bromo. 1, 2, 3, 4, 5, 6, 7. Heptano 8. So these are all pretty straightforward. All right, so next up is we're going to do your favorite thing, which is remind you of all the things that you have forgotten. All right, so you have 4 ways you know how to make carboxylic acids. We're going to go over those really quick. And then we're going to have about 2 new ways we're going to teach you how to make carboxylic acids. So ways you know how to make carboxylic acids, right? So you have 4 ways to make acids. Number 1, oxidation of primary alcohols. And I'm going to roll aldehydes in here as well. Right? So you have a primary alcohol. You use one of our strong oxidants, so KMNO4 would work. Make an acid. Sodium dichromate, sulfuric acid. We'll actually make those look like letters. So I was told in 11th grade if there are these shapes called letters, I would learn how to make them. Ha! Showed you, Mrs. Hammersmith. I didn't learn how to make letters. And I'm a doctor. So sodium dichromate will oxidize your alcohol to an acid. Or, what's it called? Oh no, I forgot. No, sorry. Chromium oxide water. Or if you have an aldehyde, remember most of our strong oxidants like KMNO4 we would oxidize an aldehyde to a carboxylic acid. Right, so that's number 1. Number 2. Ozonolysis of alkenes with oxidative workup, right? So this is when you have an alkene, you do your ozonolysis, there you go, and you use an oxidative workup. There's only one that you know, that's hydrogen peroxide. That's going to break your double bond, and you're going to turn your vinyl hydrogens, pick a different color here, your vinyl hydrogens here and here are going to become OHs. So you're going to have OH, and then you're going to keep your carbon. So you're going to have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. 1, 2. All right. So that only works when, remember, when you have vinyl hydrogens. So let's say you have something like this. All right, we're still going to break our double bond. OH2O2. There you go. Still going to break our double bond. Bam. But only the carbon that has a vinyl hydrogen is going to become a carboxylic acid. So this one becomes a carboxylic acid, and the other side just becomes a ketone. Number 3. cleavage of diols with KMNO4. Right, specifically in the secondary alcohols. Sorry if you were hearing my chair arm squeak against my desk. I'm kicking stuff. There's a audio experience for you, I'm sure. So then you have KMNO4. It's going to break this bond. And we're going to oxidize each carbon two times, all the way up to 2 carboxylic acids. And again, go back for a second. Again, just like when we had the ozonolysis, if we have, let's say, a tertiary alcohol, actually connect some bonds here. We have a tertiary alcohol. If I say it a third time, if we have a tertiary alcohol, will actually show up. KMNO4. Right, we're going to break this. The tertiary alcohol over here only gets oxidized one time. Secondary alcohol is going to get oxidized twice. That's right, so you have the carboxylic acid and you're going to have the ketone. So that's the third way you already know how to make a carboxylic acid. Number 4. Right. Oxidation of benzoic carbons. Great, so if you have a carbon, if you have benzoic carbon, and as long as it has one hydrogen on it, you will oxidize it with KMNO4 and turn it into a carboxylic acid. Ooh, it's going to fit. Great, so as long as there's at least one hydrogen, you're going to get to the exact same thing. You're going to chew off all the carbons and just be left with benzoic acid. Same deal. Acid. This one becomes an acid. That one becomes not an acid. Right? And that makes sense because, right, there's hydrogens here, no hydrogens there, right? All those positions are carbons, and you have to have a hydrogen present for you to be able to do that oxidation. So those are the 4 ways you know how to make carboxylic acids. Now it's time for the new ways to make carboxylic acids, and we're going to learn 2. Really, I'm just going to teach you 1. The second one we can kind of touch on a little bit later if need be. And that way that we're going to learn now is the addition of Grignard reagents. Oh, God. To carbon dioxide. Right, so we have a Grignard reagent, MgBr, and let's say we have, let's start with a ketone. Right, something that we know. What are we going to make? You all said you're going to make a tertiary alcohol because you're all very, very smart. So we make a tertiary alcohol. Right, and if you remember, this adds to, it's really bad, that adds to the carbonyl carbon, pushes electrons up onto the oxygen. Right, that's going to get you something that looks like this. And then the H plus comes in after you've done all your additions. And that's going to give you your alcohol. Now, CO2 is a little similar, right? So let's say we have CO2, then H plus, right? CO2 looks like this. Right? Carbon dioxide is just the carbon that is double bonded to two oxygens. I should probably put a halide on. There you go. So what's going to happen is you're going to add your Grignard reagent, and you're going to end up making a carboxylic acid. So this will add to the central carbon of CO2, push electrons up onto oxygen. You're going to make your carboxylate. In this case, it's going to be a magnesium bromide carboxylate. Right. And then again, your H plus is going to come in. And you're going to protonate that and make your carboxylic acid. So this is really kind of versatile, right? It doesn't kind of matter what your Grignard reagent is. You're always going to get the same thing. So that is great. Right? I think the thing to remember is that you're always adding one carbon when you do this. Apparently I am unable to write things that make sense. Again, the power of having shorts on. Just like, oh man, I should be being lazy. Right. Totally bailed on that first one there. Like, surprise answer. You're like, oh God. All right, so, right, see, we added this carbon right here. This carbon is the middle carbon from CO2. Same thing down here. We had 1, 2, 3. We end up with 1, 2, 3, 4. Again, the greenin is the carbon here. Hokey doke. So you're just going to add that one carbon out. So the last thing we're going to talk about today is we're just going to talk about the different types of carboxylic acid derivatives and a little bit, just a teeny tiny bit of their reactivity. Right? So we've got, I'm going to try this. We've got acid chlorides, right? So you've got carbonyl carbon right there, double bonded to an oxygen, thus carbonyl carbon, bonded to a Cl. Then you've got anhydrides. So you've got basically two carbonyl carbons sharing one oxygen. This is an anhydride because you're removing water. You're making it anhydrous, right? So to make an anhydride, you take two acids and you have water leave. We've got esters. You know esters. It's your boy, ester. We got amides of all types, primary, secondary, tertiary. So these first four, 1, 2, 3, 4, you can see how acid chlorides, anhydrides, and esters are related to carboxylic acids, right? Here's a carboxylic acid. If I can draw. Here's a carboxylic acid. We're going to come back proper here. There we go. carboxylic acid, right? All I've done is I've just changed the OH to a chlorine, to another carboxylate, to an OR, and to a nitrogen, right? Nitriles are the ones that are the carboxylic acid derivatives that kind of don't fit the mold with the rest of them. So nitriles, right? You know nitriles. There's no C double bond O. This is the one that is kind of furthest from all the carboxylic acid derivatives. But we make it a carboxylic acid derivative because you make these from amides. And so since that ties back to the amide, which ties with carboxylic acid, the carboxylic acid derivatives. All right. So the reactivity of these, so nucleophilic addition to the carbonyl carbon. Right, I'm going to put carbonyl carbon in kind of quotes because we have a nitrile in there. Right, so the most reactive, see if this will fit, that's going to be acid chlorides. Oops. Might have I actually drew the thing. Acid chlorides. Then you're going to have anhydrides will be next on your scale, followed by kind of a gap here. You're going to have aldehydes, ketones, little ketones. Another little gap, and you're going to have esters. Right. And then from there, I don't know how to do this. We'll go to the next slide here. We're going to have our ester. Right. And then you're going to have carboxylic acids. Big gap here. You're going to have amides, primary, secondary, or tertiary. And then your least reactive group is going to be your, what's it called? Your nitriles. Right, which makes sense if I'm talking about how easy it is to add to a carbonyl carbon. Probably the thing that doesn't have a carbonyl carbon is probably going to be the least reactive. But, right, so you've got acid chlorides, anhydrides, and then aldehydes and ketones. I just have these in here to kind of give you a sense of scale, right? We spent a lot of time talking about aldehydes and ketones. So these are thrown in here to kind of show that acid chlorides and anhydrides are more reactive than aldehydes and ketones. But then aldehydes and ketones are more reactive than every other carboxylic acid derivative. So you've got your esters, acids, amides, and nitriles are all less reactive than ketones and aldehydes. So I'm just putting the ketones and aldehydes there, not because they're an acid derivative, but since we've already done a bunch of work to kind of give you a sense of scale and perspective. So with that, we're going to be done for the day because, you know, I've got to get 10 lectures out of like 18 slides. So all right, I will catch you later on.